Yes, this is Life Foods from Permaculture Farmers. In this video, I want to tell about soil structure. So what you're looking at here is a sort of very typical piece of land with, as we know it in the conventional farming throughout the world. And this is a little bit clay-like soil, and it's actually from Denmark. It has absolutely no structure, to be honest with you, and you can look far and around and you will see no sign of life or anything. It is simply a desert-like thing with less than 1% of organic matter. The other, it's gone down from, in this soil here, probably 3.5. If it was a sandy soil, it would be 4.5. It's gone down all the way the last 60 years to 1% or even less. So this is the situation right now. And then, of course, if you look out of my window, this is what I see. What was once a black soil with a sort of a 30-centimeter layer of organic matter with humus is now really going white and red, and is a completely useless soil in all thinkable way. The interesting thing with this kind of soil, which are consisting of only sand, silt, and clay, is that they don't have any structure. They don't have any soil aggregation, and they don't hold. They didn't hold any water at all. All the structure and things that are made in this soil here is made mechanically with the plows and harrows and things like that. So it's loosening it up and getting some air inside. So this soil can now, as it is right now, only be grown by using artificial fertilizers, chemicals, plowing, harrowing, sowing, of course, every year. So as it can hardly grow anything else than annual crops. Inputs are excessive, and often you grow crops where you will absolutely not make any money at all on the crop. So this is the situation. And what are we going to do with it? Well, maybe we'll get to that a little bit later. So this is the sand, silt, and clay, as we know. And we have this one here, which is telling a little bit about the different thing. It is quite okay if we have the different kind of soil here. These are very difficult to work, this kind of soil, even this one, but the silt and these ones here are quite workable soils, which have good draining, at least when it comes to the silt and sand, clay. This is unfortunately this is in Danish. I haven't seen that, but anyway, this is a heavy clay, and this is very heavy clay. This is clay, and this is sand mixed clay soil, and then it's the other way around, clay mixed sand. So, and this is sand, and the one you just look at here is sand. Really much sand when it comes. So this one is down here. Silt, we don't have much of it in Denmark, but we have a little bit. So when it's only this solid particles we have a problem. There's no soil aggregation at all, and you walk out of this soil, it's like walking on the concrete. Just a little bit of rain, it's packing together, and you have no water flowing down at all. And this is what I'm going to show here. This is tomato, which is making a very typical root system as it grows a little bit into the soil, and it hits this compaction layer, which is likely to be where we're plowing to. It's also called traffic soil or plowing soil, and this one is common throughout all the conventional farming where we are actually plowing the land. It's developed very fast. It's developed with the plow and also with the chemicals we are using. There's another layer further down here. It means there's no water coming up from down there, and there's no water getting through these two layers into the ground. So if it is raining, this is obviously filling up immediately and drowning the roots. And we can see this water or this soil compaction layer is a water compaction layer, and it's blocking for oxygen. So even if the roots wanted to get down, there was nothing to go there for, because there's no oxygen. They wouldn't be able to survive. So yeah, we move on. We get some more rain, and you can see it's flooding now. Well, it's a matter of time before the plant will die. And in all cases, the water will start to run in all directions. Every spring, even in the autumn, throughout the winter, sometimes even some of the summer. In Denmark, our lands are looking like this, with a lot of ponds and a lot of water locking areas, which is not productive at all. And even though they plow and harrow every single year, they are just repeating the whole game again. Yeah. The same thing, of course, for this is what you call a dicotyledon, and this is a monocotyledon, a cereal. Precisely the same happens with the cereals. They're spreading the root in that surface. It does mean, first of all, that they have very little water available to them. If you spread the root into the ground, they would have much more water available to them and much more nutrition available to them. So what can we do with it? Yes, you probably have guessed it, that we will try to grow the soil food web. I'm not going to make a big story out of explaining it, just that by growing the soil food web, we get the soil, we get some organic matter into the soil, and we get all of these microorganisms to function, and the result is quite simple. The plant will break through and start to grow into the ground, and this can happen in the same growing season. So if you add this thing on the crop looking like this, that will be a compost extract. If you can see, oh, this is not good, you can take the penetrometer and go around and check out how deep this thing can grow down, and even reach 170, the roots will not go through. You can try to dig down and see, does it look like it has no oxygen? And then you add the compost extract or compost tea on to the crop, and the plants will start to break down through, because the microorganisms are loosening up the soil and start forming soil aggregation. Yeah, and again with the dicotyledon, it goes down and spreading out all over the place. Yep, there's a sort of a cartoon-like picture of it. So this is the situation we have been talking about until now. And here we are starting to develop the soil, and this is now in the form of a soil profile. Because you can see worms are running up and down, roots are going into those channels the worms are making. And this is what happens for thousands and other thousands of years. And if you go out and dig a soil profile in any field, anywhere, you will find this when you get down through the top layer of where we are plowing. You will get down to this so-called undisturbed layers of soil. And then you will find the profile. If you make a profile half a meter or 70 centimeters wide, you'll find roots, dark stripes of things going all the way down across into the ground. And that is those ones we have here, which is channels of which there have been growing maybe thousands of trees up and down, and earthworms and everything has been running up and down for many thousands of years. And they have been taking nutrients from down, deep down in the soil, and put on the top, made available here. So further, there's more development of this. We're starting to get some different, at least we should start to get some different fungus and bacteria, but at least the development is here, it's visible. And finally, we have a pretty good soil profile. You notice that this one here, these lines are disappearing, and they are disappearing. The worms and the microorganisms are simply moving it and opening up and make a soil, a biological soil layer, which is going deep into the soil. So yeah, enough about that. So furthermore, we can have mycorrhiza, which are also improving on the on the soil. So the plants are growing. And then if we have a constant plant cover on our fields, the mycorrhiza will grow in and extend the root system with up to 800%. And this is explained in many different ways how this mycorrhiza is working. But anyway, I think that there are two different kinds. One are growing into the plant, the other one is growing on the surface of the plant, and it's a little bit different where they are, and it's not so important here. But this is the example. Here we have the typical roots. This is a root tip. You can imagine this very small thing. We look there, so it's zoomed up 100 times here. And then there's the root hairs are going out, and it does catch on to a little bit of fertilizers here and there. But if it has a mycorrhiza, it is then extended with this, what we say, 800%, and it gets all the way into the soil aggregates and things like that, and mineralizing the fertilizer. So this when it looks like this, it needs to be given fertilizer. You need to keep the pH and all of these many different input. Here you need to maintain your soil. You should really see yourself as a soil farmer. And that will, if you grow your soil, if you look after your soil, you have good farming and very good crops, high quality crops. Yeah, and there's a good example. Biocomplete compost. It's a bit dark in color, but it's probably the picture. It looks a lot like worm casting. This one here, if you ask me, but it surely looks nicely. Only if you take a look at it with a microscope, you will be able to see if it actually is biocomplete. It's not going by the look. This could be full of actinobacteria, and it can have been grown under rather anaerobic conditions, and maybe it hasn't been hot enough and so on. This has probably been very well. This one here looks okay. Normally you can see it also if a compost is not okay. You can easily see it. Also without having something to compare to, if you get a little bit of experience. If I walk by a stack of compost, I can not only smell it, I just have to touch around in it, and I can see very easily if the compost is okay or it's not okay. Not only if I see fresh plant material, of course it's not composted, but I also see when it's composted, if it has the wrong smell, if it has the wrong look, I'll know immediately. So that's an experience we can get easily. I think it comes natural to people to we somehow understand if something smells good or it smells bad. We should keep our mouth or fingers away from it. And if it smells, what can I say? Okay, we know it. I don't know, instinctively, I think in some way we know it. Actually, the compost, it smells nice. It's enjoyable to smell. So it has no strong smell or anything. There you go. A doctor named David Johnson making a lot of different tests here, and has come very far with doing this. This is his starting point when he starts out, and he do a 3.5-year study here in a small plot. Remember, this is how it looks, and this is the compost treated, and he have a 7-inch. 7 inch is something like, I think it's about up to 20, maybe 20 centimeters. It is what has developed of the change from this to this. A lot of organic matter, and the root system are growing down, and there's a control thing in somewhere else where they're probably not really, I don't get the information on what exactly they do with the control. Maybe this is just the same small plot with that is not treated at all. I think it is. Yeah. So we get it. So what does he make? He makes this thing here. What do we make when we grow this thing? We want to make a soil aggregate, and we have the soil aggregate contains of well, they write it down here, but it contains of different. If you look at this, zoom out of this little spot here, it contains of sand and silt particle, microorganisms, 1 to 20 aggregates, debris, organic matter, water, hyphae, and you go up and look here. This is the mycorrhiza, hyphae, debris, and organic matter again. So we get it. It is so that the bacteria are making some kind of a glue film which are keeping these ones together, and the fungus are making some even other ones which are keeping it even more together. And then of course you have the roots going in between, and there's some pores which are air, and it is water which are inside here. So it's very, very, very important. And this is why there's a difference between this, what we call sort of salt structure of soil, which means it's just the silt, the sand, the clay moving around. You can sort of take it up and take it out with your hand. It will not stick together in any way. This one here will stick together, and it will hold a lot of nutrition. Every one of these very small particles we see here are having a negative charge. So when there are some nutrition which have been released by the microorganisms from the sand, silt, and clay, this will stick on to the soil aggregates. So it's not going to get washed out. It's going to be sitting there until the plant picks it up with the root in exchange for what you call haste molecule and getting it on there. Okay. Yeah, we're going to look a little bit at what is all these things I think should be inside when I talk about the soil food web. So I have taken some pictures here. Here you see a stegosaur, some fungus, and another bit of fungus, and testate amoeba here. There's quite a lot. You see all of those small dots that are sort of you can see the site and so on. This is actually bacteria. So there's quite a lot of bacteria here. There's another one looking a little bit like a stegosaur out of focus here. Down here we have at least something here looking like an amoeba cyst. It's not an mite and a microarthropod. There's some parts of an insect here. It looks very interesting, but it is really nothing else than insect that has fallen apart. But here's what could be fungus, but it's not really regular. So actually I wouldn't count it to be a fungus. But this one, I would count it to be a fungus, and I see what we call septas, even septas and so on. So I like it. I like it a lot. This one there is so small that maybe I will not count it. Just think this might be a fungus, but it's not big enough for me to say, okay, this is a fungus. And we have another fungus down here, and we have something here that looks a little bit like a testate amoeba. At the same time, it doesn't really look like enough like a testate amoeba. It is so that some of those ones here are quite obvious to see what it is, but really I'm not very happy with identifying things which is on pictures. I think it is very unprofessional to take in pictures and try to look at them, because I work so much with my microscope up and down to focus and zoom in that I think that to do it on a picture, even though I'm trying to take good pictures, I do. But really you would not be able to come with a professional explanation of what is here. There might be twice as many bacteria here, and you might have a whole fungus laying a little bit down in the layer. You might look at this one here, get it into focus, and it might turn out to be a fungus also. Right now I think it looks more like a piece of plant debris. You look in underneath this one here, you might easily find that fungus are growing in and out of this one. So only by focusing up and down in those 0.15 millimeters. And really it is to look down from the top of, if you look into a forest or a jungle from the top and down, this is how this thing looks when you come into it. So you see this three-dimensional picture, which is you can zoom up and down into it. So, and a lot of different things are turning up. It doesn't mean we can't tell a little bit with pictures, but it doesn't sort of give the full picture, the full view. Another one, we get a little bit closer to them, is a fungus. This is without the slides, without the fungus even still. It's a dower thing. It's sort of what it looks like, again, I would say. And there's a testate amoeba. Those ones are without doubt the testate amoeba and the mycorrhizal fungus. This is a bacterial nematode, and this is a celiac, which is running around, and this is a naked amoeba and a flagellate. And all of these ones, this one eats maybe, I think it's up to 30,000 bacteria in a day. This one eats 10, and this one also eats maybe 10. I don't know, this one eats 10, and so on. And the testate amoeba will eat 10,000. And all of them, they poop out a lot of manure or waste, or what you call it. And that manure and waste is plant nutrition that is available to the plant. And that's the reason for that the plant want to grow all of these different microorganisms, especially the fungus and the bacteria around its roots, because in that way it feeds all of these ones here which are eating the bacteria. It makes a microenvironment for them just around the root, and the fungus and the bacteria are able to mineralize the soil particles. The sand, silt, and clay can be mineralized, and that will make the nutrition available to the plant. Let's move on. Okay, here we go. Mycorrhiza on a picture, 800% extension of the root system. Mycorrhiza we don't make with compost. Some people think that we don't. We make it by growing a cover crop in our fields, or by growing perennial plants around fences and things like that. Permanent plant growth make mycorrhiza in the fields very, very beneficial for the plants, or for those plants who grow with them. One family don't grow, the whole Capis family don't grow with mycorrhiza, but almost all the rest that I know of do. Here's another example where it comes more clear. So yes, this is about what I want to tell about the soil structure, and this is more about how we make it, obviously, than it has been about soil structure itself. We make it by adding biology to the soil, so we can quite easily regenerate soil structure. We can do it in 1 to 3 years, as you can see here. Dave Johnson have done quite fast. In 3.5 years, he gets some soil structure, and so this is what we can do. So if you want your soil structure to be regenerated somehow, you got to contact me on Permaculture Farmers COM. So yeah, that was all. Thank you very much for now.